The following commands use pip, a package management system in Python, to install two Python packages named cats and termocolor.
The cats package focuses on time series analysis, forecasting and visualization, while the termocolor package is intended for styling text output in command line interfaces.
This code imports essential Python libraries for data visualization and analysis.
It includes Seaborn for statistical graphics, Pandas for data manipulation, Matplotlib for creating plots, and termcolor for colored terminal output. These libraries are widely used for tasks related to data visualization and analysis. When this code is used, the visual design of plots created using the Matplotlib library will be changed to the Seaborn style.
This style offers improved aesthetics and color schemes, resulting in visually pleasing visualizations that differ from the default Matplotlib styles. This code uses the Pandas library in Python to read data from a CSV file named pg.csv and store it in a DataFrame. It converts the date column in the CSV file to dates using the parse_dates parameter.
The index_col parameter is used to set the date column as the index of the DataFrame.
Finally, the code displays the DataFrame df that contains the data from the CSV file, with the date column set as the index. The code is using the augmented Dickey-Fuller test to analyze a financial data frame containing columns like open, high, low, close, Adj Close, and volume. This test checks for a unit root in time series data to ascertain if the data is stationary. For every column in the data frame, the code uses the add_fuller function to determine the test statistics of p-value, number of lags, number of observations, and critical values at significance levels of 1%, 5%, and 10%.
Afterward, the results are organized into a data frame to enhance their presentation. Finally, the program displays the column name in red and provides the results of the augmented Dickey-Fuller test. This includes the test statistics, p-value, critical values, and other relevant information. This code is used to check if the financial data in the data frame is stationary. It does this by performing the augmented Dickey-Fuller test on each chosen column.
This code utilizes the PowerTransformer tool from Scikit, learn to apply a Box-Cox transformation to the dataset df.
This transformation is used to make the data distribution more similar to a normal distribution.
The resulting modified data is saved in a new data frame named df_power_transformer, with the specified column names, open, high, low, close, Adj Close, and volume. This code iterates through a list of specified column names.
It then performs the augmented Dickey-Fuller test add_fuller on the data in each column after applying a power transformation. The test results are printed, displaying the test statistics, p-value, number of lags and observations used as well as critical values at various confidence levels. This operation is carried out for all columns listed in the columns list.
This code uses the statsmodels library to create autocorrelation function plots for each column in a data frame called df.
The autocorrelation function ACF helps understand the relationship between values in a time series and their past values. The code processes each column in a data frame, computes the ACF using a lag of up to 50 periods, and generates individual ACF graphs for each column with the column name as the title. After each ACF graph is plotted, a blank line is included between them to help distinguish them more easily.
This code uses the seasonal decomposition method from the statsmodels library to break down multiple financial market data columns like open, high, low, close, adjusted,
close, and volume into three components: trend, seasonality, and residuals. Then visualizes these components for each column in a plot. To analyze data, this process creates separate plots for each column showing trends, seasonality, and residuals. The title of each plot is styled with a specific font and size.
Using matplotlib, these components are then plotted, displayed, and additional lines are added between plots for better clarity.
This code uses the fast Fourier transform technique to identify seasonal patterns in time series data. To simplify, the code initially reads a CSV file with time series data, filters only the date and volume columns, and subsequently changes their names to time and value respectively. Then, a time series data object is generated from the data. The FFT detector is applied to the time series data object to identify and examine any seasonal patterns in the data. This code reads specific columns from a CSV file into a pandas DataFrame and renames the columns. It then uses this DataFrame to create a time series data object. First, an FFT detector object is created using the time series data object. The detector method is then used on the FFT detector object to identify any unusual occurrences or recurring patterns in the time series data, utilizing the fast Fourier transform FFT algorithm. This code processes a CSV file with stock market data.
It extracts the date and closing price columns, renaming them time and value. Finally, it generates a time series object using this extracted data. Following this, the fast Fourier transform FFT algorithm is employed to identify any irregularities or uncommon trends in the time series data. By utilizing FT, sudden and unexpected alterations in the data are pinpointed, which could suggest anomalies like sudden spikes or drops in stock prices. To conclude, the code invokes the detector method to carry out anomaly detection using FFT on the time series data. This code probably uses the sklearn library in Python to create a power transformer. A power transformer applies mathematical transformations like log or square root to the data, aiming to make it follow a normal distribution. This transformation can enhance the performance of certain machine learning models that rely on data being normally distributed. This code calculates the difference between consecutive values in a DataFrame column named df_power_transformer, with a difference period of 1. The differences obtained are stored in a new DataFrame named diff_series. To avoid missing values that may arise from the differences, the dropnet function is applied to remove those rows. The code is performing an augmented Dickey-Fuller test on each column of time series data. First, it takes the first difference of the series to make it stationary. Next, it iterates through each column such as open, high, low, attest statistics, p-value, number of lags, number of observations, and critical values at different significance levels. Finally, the results for each column are printed after the first differencing step.